All right, good morning, everyone. Today will be our last lectures. Okay, but before we do that, let's talk about the schedule for the last 2 weeks of this semester. Okay, so Monday, November 30th, will be a research paper presentation from Group A and B. Okay, so please. You can email me, share with me your PowerPoint presentation, and during the presentation time, I will let one of you be the host for the meeting, so you can control the screen, and also you can control the progress of the PowerPoint presentation. Okay, so yeah, especially for Group A and B. Okay, make sure you do that before Monday, your presentation time. Okay. Wednesday next week, December 2nd, will be presentations from Group C and D. And then Monday, December 7th, will be presentation from the last two groups, Group E and F. Okay. And then December 9th, we'll do our final review. Okay, December 9th is the final review. Okay. So for today, we're gonna finish our final lectures. We talk about asphalt concrete, and then we're gonna finish talk about the questions in the midterm. We have a couple of calculation questions to be discussed for the midterm presentation. Okay. All right. So let's get started. So lecture number 22, asphalt concrete. So last time, lecture 21, we talked about asphalt binder, and we know how to select different asphalt grade depending on the local climate. Remember the last questions we discussed. Okay, asphalt concrete is asphalt binder plus aggregate, same to Portland cement concrete. For Portland cement concrete, we have Portland cement binder, which is a mixture of Portland cement plus water plus any mixtures. Okay. Also, we have sand and coarse aggregate in Portland cement concrete. Asphalt concrete is mixed under high temperature. The reason for that is, again, at room temperature, asphalt binder is semi-rigid. It cannot be mixed with sand and coarse aggregate. It need to be heated, or we use car bag or emulsifying agent to liquefy the asphalt binder so it can be mixed with aggregate. Okay, so asphalt pavement is also called flexible pavement. Okay, for Portland cement concrete pavement, it is called rigid pavement. Because asphalt is not a totally rigid materials. It's a semi-rigid materials. Okay. And flexible pavement, also called hot mix asphalt, HMA, occupy more than 90% of the paved road in the US. Okay. The desired property for hot mix asphalt concrete pavement is stability, which means it need to resist the permanent deformation under load, and also fatigue resistant. The road will under repeated loading, so fatigue resistance is very, very important. And also resist to thermal cracking, because when we have temperature change, it will contract or expand based on temperature. Okay. It's easy to get crack at low temperature. Okay, because at low temperature it becomes more rigid. Okay. And also resistant to hardening or aging, both during production period and during the service period. Remember last lecture we talked about the rolling thin film oven test or RTFO test, which is simulation of the aging process during the production day. And also we talk about the pressure aging vessel tests. This is simulate the aging process during the service life. Okay, so aging process is very important for asphalt binder. Also resist to moisture induced damage. We call that stripping. Stripping asphalt from the aggregate. This is kind of similar to debonding of the Portland cement paste from the aggregate. Okay. And also skid resistance. We check the texture surface of the asphalt pavement. Also workability. Okay, so workability here means how easy we can mix asphalt binder with the aggregate, and how easy we can place and compact the asphalt concrete. Okay, so this is similar to the slump test for the Portland cement concrete, and also the cost of the materials. So based on the above performance requirement, we have this HMA design criteria, including stability, long-term performance, which is fatigue, thermal cracking, we also call that temperature sensitivity, okay. Moisture-induced damage, this is the debonding between the asphalt binder and the aggregate, also called stripping, skid resistance, workability, and also load capacity. Okay, so these are the design criteria for hot mix asphalt concrete. Okay, but in this class, we will not go into the details of how to design asphalt pavement. The design is called super pave mix design, which is not covered in this class. Okay, so we'll take CE461 or I think maybe 361. It will talk about how to design asphalt pavement. Okay, this is a pavement engineering class. In this class, we will focus on materials properties. Okay, so let's look at in general the preparation process when we prepare the hot mix asphalt pavement. Okay. First of all, we need to prepare for the aggregate. We need to crash, screen, and also storage of the aggregate. Okay. Aggregate need to be proportioned depending on the mix design. Okay. And also a special treatment for the aggregate is drying and heating. Okay. If we have moisture on the aggregate, it will cause debonding or stripping of the binder from the aggregate. This is different from Portland cement concrete. For Portland cement concrete, we don't really care about make the aggregate dry. It can be have some moisture, like wet condition or oven dry or air dry condition. We only need to do the moisture adjustment. But for asphalt concrete, we need to dry the aggregate. So this is one of the major difference on the aggregate side. And also the aggregate need to be heated up. The temperature need to be high because again, asphalt cement need to be heated to reduce the viscosity so it can be mixed with the aggregate. Okay. And then the storage and heating of asphalt cement. Okay. And we measure weight and mix of the banded aggregate with asphalt cement. Okay. And also loading, transport, and paved asphalt concrete. Okay. So aggregate must be heated to the required mixing temperature. Okay. Two purposes. One is to drive off the moisture, and the second one is to maintain the same temperature with asphalt cement. Okay, so we can mix asphalt binder with the aggregate. Okay. And here shows us, what are the heating methods could be used for the asphalt aggregate. here is a picture of aggregate heating. Okay, this is the aggregate conveyor, and we have dust collector, and the aggregate is heated up in this big oven. Here talk about more details on aggregate production. The clay on the surface of aggregate can cause problems such as stripping or debonding. Okay. Another potential problem is clay may make the asphalt cement swell and emulsify the binder. So emulsify means make the binder soft. Okay, so which is not good. Okay. And dirty aggregate can also reduce adhesion of the binder. Okay, so we need to clean the aggregate before mix with the asphalt binder. All right. Next, let's talk about the gradation of asphalt concrete aggregate. Okay, so gradation is very important for asphalt concrete. It is actually more important compared with the gradation for Portland cement concrete. The major reason for that is because for Portland cement concrete, the cement paste is very strong. It can take a lot of load. But for asphalt binder, it is semi-rigid. It's kind of soft, so it cannot take the load by itself. Okay, so the load transfer depending on the gradation or the interlock between the sand and the coarse aggregate. So that's the reason why gradation for aggregate in asphalt concrete is very, very important. Okay. So basically we have three types of gradation. We have uniformly graded, okay, which means we have few point of contact, like we can see in the first picture on the top right. The interlock between aggregate is not very good, and also asphalt concrete we have high permeability. The second one is called well graded. We have small, medium, and large size of aggregate. We have good interlocking between the aggregate, and also the concrete has low permeability. The third one is called gap graded. In gap graded, we only have small sand and large coarse aggregate. We don't have intermediate size aggregate. The concrete may also have good interlocking. The permeability could also be pretty low. All right. So this is the cross section of asphalt concrete with dense graded. Okay, we call that dense graded mix. Okay. All right. For the dense graded, the sand, the coarse aggregate is in control. Okay, so the sand will carry most of the load. For coarse aggregate, there are not too much coarse aggregate in the system. So there's no interaction or no particle-to-particle contact between coarse aggregate. So sand will take most of the load. So this is called dense graded mixes. This is belong to the second category, belong to the well-graded mixes. It has both the coarse, intermediate, and small aggregate. The next one is called coarse graded mixes. It also belongs to the well-graded category, the second category. In this gradation, both coarse aggregate and fine aggregate will work together. They will take the load together. Okay. For coarse aggregate, because we have a higher percentage of coarse, we have some particle-to-particle interaction, contact between coarse aggregate. And this one, we can see, obviously we have much more percentage of coarse aggregate, and we call that gap graded mixes. So for gap graded mixes, the coarse aggregate is in control. They take the majority of the load transferring. Okay. So we have a lot of particle-to-particle contact between coarse aggregate. Okay. So which type of gradation we choose for asphalt pavement depending on information such as the thickness of the pavement, okay, and also some other information. Okay. So as you can see, the gradation for aggregate in asphalt pavement is very strict. Okay. Again, the major reason is because aggregate will take most of the load transferring job. Okay. Asphalt binder is very soft. Okay. Here is about the preparation of asphalt cement, the binder. Okay. Again, we need to heat it up so we can make it soft to mix with sand and coarse aggregate. And also we need to ensure we have sufficient uninterrupted mixing. Okay. We should have continuous heating the binder during the storage process. Okay. And also we need to ensure we have enough asphalt for continuous mixing. And here is the drum mixer plant, which is the oven to heat up the asphalt binder. All right, so now the next couple of slides, let's talk about small calculation problems. This is how we calculate the density and voids for asphalt concrete. Okay, let's look at the picture on the right. So here shows what are inside asphalt concrete. We have aggregate, which is here. The majority of the volume is occupied by aggregate. And we also have asphalt binder, okay, which have two parts. Okay. One part is called absorptive asphalt binder, which is the asphalt absorbed on the surface of aggregate. Okay. We also have asphalt binder, which is VBE, which is E is for effective. So that's the asphalt binder which is not absorbed on the surface of aggregate. We also have a small percentage of air voids in the system. Okay. The percentage of air voids is very important for asphalt concrete because the more air voids, the more aging process, the faster the aging process, because in the air we have oxygen, and oxygen will accelerate the aging process for asphalt concrete. Okay. So because of that, we have many different type of voids. For example, the voids in the total mix. Okay, the void is in total mix is equal to VV, which is here VV, the volume of air voids, over VM. VM is the volume of voids plus volume of BE, which is effective binder, plus volume of VS, this is the volume of aggregate, which including the volume of aggregate plus absorbed asphalt binder. Okay. The volume mineral aggregate, VMA, is defined as VV, which is volume of air voids, plus VBE, which is volume of asphalt binder, over the total volume, so volume of mix VM. Okay. And also we have what filled with asphalt. Okay. Again, the reason we care so much about the void in asphalt is because it is closely correlated to the aging process of asphalt binder. Okay. All right, and here shows an example of small calculation. So we have asphalt concrete, mix including 94% of aggregate by weight, and the specific variety of aggregate and asphalt is also given, 2.65 and 1.0 for asphalt. Also tells us the bulk density of the mix, 147 pounds per cubic foot, and tells us ignore the absorption. So absorption here, absorbing asphalt binder will be ignored. Okay, and the question is asking what is the percent voids in the total mix, or VTM. Okay, so the VTM is defined here. The volume total mix is equal to VV, which is the volume of air voids, over Vm, which is equal to volume of voids plus VBE, asphalt binder volume, plus Vs, which is the volume of aggregate plus the effective binder, absorbed asphalt binder. Okay. For these kind of questions, what we normally do is we assume a certain unit volume, a certain unit weight of materials, and then based on that, we calculate how much weight or how much mass for each type of materials, and then we calculate the volume for each type of materials, and from there we can do the calculation. Okay, so for example, here we assume the total volume of the mix Vm is equal to 1 cubic foot. Okay, and then we can determine the mass for each type of component. So the total mass of the mix is equal to 1 cubic foot times the unit weight, 147. So we have 147 pounds of asphalt concrete. 94% of asphalt concrete is occupied by aggregate. So the weight of aggregate is this much. And then the remaining 6% will be asphalt binder. So we have 8 pounds of asphalt cement. And then based on the weight, the mass, we can calculate the volume, right? So for aggregate, the total weight divided by 2.65 times 62.4. So this is specific gravity for the aggregate. This is density of water. So this is the density of aggregate. So the mass divided by density, so this is the volume occupied by aggregate. Similarly, we can calculate the volume occupied by binder. So it's 0.141 cubic foot. So the question tells us to ignore the absorption. So the effective binder, VBE, will be the same as volume of binder. So 0.141 cubic foot. So the remaining volume will be occupied by voids. Okay, so again, this is similar to what we do the calculation to the mix design for Portland cement concrete. The last step is we calculate how much volume is occupied by sand by doing the subtraction. So the total volume is 1 cubic foot minus the volume occupied by aggregate minus the volume occupied by binder. So volume of voids is 0.032 cubic foot. So we can calculate the volume, VTM, the volume of total mix. Okay, from there is 3.2%. All right. The final part of this lecture, let's look at the pictures of different type of asphalt concrete distresses, different type of cracking. All right. So this problem is called rutting. Okay. So rutting means when the viscosity of the binder is too low, okay, below the optimum range, due to reasons such as we don't have enough compaction, or the temperature is too high, okay, the asphalt becomes soft. So this is the wheel. The wheel will cause the permanent deformation of the pavement. Okay. If the subgrade is soft, the rotting will look something like this. Okay. If the subgrade is rigid, then the rotting will be something like that. Again, this is because the viscosity of the pavement is too low. Right. Here also showing the picture of rotting. Okay, we can see it could cause potential problems, safety concerns, because after raining, this area will fill with water. So we could have hydroplaning, which is the water layer between the tire and the pavement. So this is very dangerous. All right, this is also rotting problems. So we also have another name for that. It's called pushing. Okay, asphalt is just too soft. All right, and here we have another type of deformation. It's called shelving or corrugation. Okay, as probably you can see here, we have stop sign here. Okay, because in a stop sign, the vehicle often do the stop and moving. Okay, so this is stop and moving motion will cause asphalt to crack. And crack will be patterns like this. The direction of the crack will be perpendicular to the direction of the pavement. Okay. The reason for that is because the asphalt is too soft, or we have too much moisture underneath the pavement. This is called fatigue cracking. Okay. Fatigue cracking is caused by repeated traffic loading, okay, and also because the aging process of asphalt. The asphalt become too rigid, and that will cause asphalt to crack under fatigue load. Okay. The cracks will be interconnected to each other. Okay. Like we can see from here, this is a very common type of cracking for asphalt. I believe everybody has seen that type of cracking before. And also here, so fatigue cracking. This is the rotting caused by soft asphalt together with fatigue cracking. Okay. So if the fatigue cracking become too severe, part of asphalt can be spot off, and we have potholes. This picture has cracks which is perpendicular to the direction of the pavement. This is caused by temperature change or thermal cracking. The reason for that is because we have temperature change during winter or summer, and the viscosity of the asphalt binder is too high, or we have aging problems for the asphalt, which cause the viscosity to increase. So this is another picture for thermal cracking. Again, the pattern's direction, the crack direction will be perpendicular to the direction of the pavement. In this picture, the direction of crack is parallel to the direction of the pavement. We call that longitudinal cracking. Okay. This is another type of fatigue cracking due to repeated loading. And this is another type of crack called reflective cracking. Okay. In this asphalt concrete, we have two layers. The top layer is made by asphalt, and the bottom is made by Portland cement concrete. Okay. So when we have a Portland cement concrete underneath, and the Portland cement concrete may crack due to many different reasons, and that will transfer the cracking into the top asphalt layer. So we call that reflective cracking. Okay, here is another picture of reflective cracking, and we can see above the joint of Portland cement concrete, we have this cracking above that joint. Okay. This is also interconnective cracks. Okay. Due to concrete become aging, too old, shrinkage of the pavement, or we have too much temperature cycles. Okay, the binder become aging and too stiff, too rigid, and that will cause the asphalt concrete to crack. Okay. We also call that block or mat cracking, so we can see the crack will interconnect to each other. This is another type of cracking which only occurs at the edge of the pavement. We call that edge cracking. This is caused by lack of lateral support or the settlement of the base materials. Okay, we have settlement of the base, which will cause cracking at the edge of the asphalt pavement. And this is potholes. Okay, everybody knows potholes. This is caused by fatigue cracking. Potholes only occurs in thin asphalt pavement when the thickness of the pavement is only about 1 to 2 inch. Okay, so this is again a result of fatigue cracking of asphalt pavement. Okay, so we have spot off of a small piece of asphalt from the remaining pavement. This is potholes. And the final picture is shown here is a pop-out. So some of aggregate is reactive, okay, similar to what we discussed in ASR or alkali-silicate reaction between aggregate and Portland cement concrete. So in asphalt pavement, some of aggregate may also be reactive, which cause expensive cracking, and they may be pop out from concrete. Okay. All right. Okay. So that's the end for the lecture, which is our last formal lecture for asphalt concrete. We have around 17 minutes left, so let's talk about the midterm. All right. See, last time we stopped. Sorry. All right. So we stopped here. I hope you can see the picture. Share the screen from my iPad. Okay. All right. So this is the last one of the calculation questions about mix design and how we do the moisture adjustment. Okay. Make sure you review that questions. Okay. So in this question, we're giving the stockpile weight of the sand and coarse, and also the oven dry weight of the aggregate, absorption capacity, and the density. Okay. The first part of the question asks to describe the field moisture condition. Okay, so some of us just describe we have oven dry, we have air dry, and we have wet condition and SSD condition. But here I'm asking what are the moisture conditions for these two aggregates. Okay, so there's many different ways to do that. Here shows one of the ways. Okay, they calculate the weight of saturated surface dry condition of the aggregate, okay, which is equal to the oven dry weight. Okay, the oven dry weight times 1 plus AC. This is absorption capacity. Okay, so that will give the SSD weight of the aggregate. So for the SSD weight of sand is 987.6 grams. Okay, so we compare that with the stockpile weight. Okay, so if it's smaller than the stockpile weight, that means the stockpile aggregate is in wet condition. If it's larger than stockpile weight, then it will be in air dry condition. Okay, so for coarse aggregate, again we do this. Okay, so stockpile weight times 1 plus AC. So the SSD weight is again smaller than the stockpile weight. So the coarse aggregate is also in wet condition. Okay. So the next part is asking what is the water to cement ratio of the aggregate of the concrete. So the water to cement ratio, remember, does not change depending on the moisture condition of coarse aggregate and the sand. Okay, so that's the exact reason we do the moisture correction. So how to calculate the water cement ratio is very simple. We just use the weight of water divided by weight of cement. So 0.6. Okay, 0.6 is not, should not be that. Okay, so 0.6 we just use 300 times 500. So that is the water cement ratio, what we designed. Okay, do not do the moisture correction. The next part is to adjust the moisture condition. Okay, so for moisture condition, we need to calculate MC, okay, which is W stockpile, okay, minus WSSD. This is W stock minus 987.6 is WSSD. Okay, divided by WSSD. So this is the moisture content. And we use moisture content to times WSSD. So that is how much moisture in the sand. Okay, and that value plus WSSD, this is how much stockpile aggregate is needed. Okay, so do not confuse moisture content with things like absorption capacity. So do not use that to do the moisture adjustment. Okay. And similarly, we can do the moisture correction for the coarse. Okay, so this is plus 10.88 pounds. So that's plus. Okay, so we need 1710 pounds of gravel. And that moisture will be minus from the mixing water. So we make sure the real amount of water in our concrete is exactly 300 pounds. So we do not change the water to cement ratio in the system. Again, that's exactly the reason why we do the moisture correction. Okay. If we change the water to cement ratio, the strength will change. Okay, so everything will change because water cement ratio is the most important parameter in our concrete mix design. All right. Then next part, asking to calculate the air content of the concrete. You know, for this type of calculation. What is the volume of a certain component in a system? So we calculate the volume depending on the mass and the density. For example, the mass of cement is 500 pounds. The density is given 196. Okay, so that's the volume of cement. So you also can calculate the volume of water, volume of the sand, and the cars. Okay, so the only remaining volume materials will be the air. So we use the total volume 27 cubic foot minus the volume of all these components. So we have 0.42 cubic foot of air in the system. Divided by 27 total volume, so we have 1.56% of air by volume. Okay. Next question. This is ask us to calculate the volumetric strain in a cylinder. Okay. In a class, I'll show you the equation for the volumetric strain. The strain, volumetric strain epsilon V is equal to the strain in X, Y, and Z direction added together. Okay. So this is a cylinder. Okay. For the cylinder, we have the strain in X, Y, and Z direction. Okay. So let's see, this is X, Y, and Z direction. Okay. So the compression is in the Z direction and tells us the axial strain is 600 times 10 to the power of -6. Okay, and also tells us the Poisson's ratio is 0.18. Okay, so here the volumetric strain in the Z direction is this much. Okay, and this is under compression. For the strain in X and Y direction, okay, it will be expansion, right? So horizontally, the cylinder will try to expand. So the strain in the X and Y direction will be 600 to the power times 10 to the power of -6 times the Poisson's ratio, 0.18. Okay, but it will be the opposite. Okay, if you see compression is positive, then in the Y and Z direction, it will be negative. Okay, this is the same for strain in X and Y direction. Okay, so the right answer will be 600. So that's strain in the Z direction minus the strain in the X direction, and the Y direction will be the same, so times 2. And don't forget this is minus. Okay. You can do similarly. You can assume what is the initial volume. Okay, like what we can see here. So this is one of the better ones calculation from our one of our students. Okay, so the lateral strain is this much. Okay, but don't forget this should be the negative. So we can, based on the initial volume and the final volume, we can also calculate how much change in the volume, and then we can calculate the volumetric strain. Okay, so very good try for this example. The final questions to calculate the porosity. Okay, so the capillary porosity, given the definition, is equal to the pore volume of capillary pores divided by the total volume of hydrated cement specimen. So this question is kind of hard, but I only give 1 point. Okay, so the capillary pore volume equation is shown here. So VC is the volume of capillary pores, okay, which is a function of water-cement ratio and degree of hydration alpha. Okay. The question also tells us specific gravity of cement, degree of hydration, 90%, and also the porosity of 0.12. Okay. All right. So calculate what is the water-cement ratio here. Okay. So again, for this type of questions, okay, we can assume a unit volume or a unit weight of certain component. For here, I just show you, we just assume we have 1 gram of cement. Okay. So if we have 1 gram of cement, so this cement, so we have 1 gram. And for water, how much we have? We have W over C gram of water in a system. Okay. So we mix 1 gram of cement with W over C gram of water. We can calculate the volume of the cement paste. Volume of paste. So the total volume, right, is equal to volume of water plus volume of cement. Okay, so the volume of cement is equal to 1 gram divided by 3.15. So this is the specific gravity of cement, which means for 1 cubic millimeter of cement, the weight is 3.15 gram. Okay, so this is the volume of cement. The volume of water is equal to the mass of water, so it's W over C gram of water divided by the density. The density of water is 1 gram per millimeter of water. Okay, so the total volume of the paste is much. Okay. For the porosity tells us is equal to capillary pore volume divided by total volume of cement. Okay, so the capillary pore volume is equal to VC, and that equation is also given us here. Okay, divided by weight total. So VC is equal to W over C based on that equation, minus 0.36 alpha. And V total is here, tells us. Okay. So, and that is equal to 12%. The porosity is equal to 12%. All right. So plug in this number, the only unknown will be water to cement ratio. Okay, then we can calculate how much water cement ratio is the system. Okay, all right, so that's the discussion for the midterm. For us to prepare for the final exam, I will give you a sample final exam, and together with the answers, we're gonna have more discussion when we do the final review on December 9th. Okay. All right. So that's the end for today's